with our humble or not so humble institute. So thank you very much.
Thank you very much, David. It's a real pleasure to be here. The last time I was here in Northeastern was, I think, 4 years ago, and this wonderful institute and the space here hadn't been put together yet, nor the Network Science PhD program. So I'm always really pleased to hear about all the exciting things going on here, and it seems like there are just incredibly exciting things here. So this talk is titled "Somewhat Provocatively, the Trouble with Community Detection." I will tell you what some of those troubles are. But first, I want to do an advertisement, which is this is a different project that I won't be talking about anymore today, which is the Index of Complex Networks. The goal of this project is to index all the network data in the world in one place. We're not a repository. We don't store the data, but rather we're like what Yahoo was in 1997. Except with a better interface. So right now we have, this is actually a little bit low right now, we have over 450 data sets that are indexed, and each data set can include multiple networks. So we have something like 3,500 different networks available across these different data sets. And they're distributed over all different types of domains. You can search based on the properties like bipartite or metadata or whatever. Please, if you like data, feel free to use the site. You can also contribute to it. You can make suggestions for networks to index. There's a form you can fill out with some information. This is meant to be a community resource to help us be able to easily find data that you can use to test our methods or investigate the phenomena and so on. Okay, so what is community structure? Maybe many of you know what this is. I will give you my perspective on this. It starts with recognizing that real-world networks are these complicated objects, and we want to understand them. And so, if you draw one on the page, you get what people sometimes call hairballs, or what Mark Vidal many years ago coined the wonderful term ridiculogram to describe these kinds of pictures. And thankfully, these aren't required portions of papers anymore. But the questions that we often are interested in are questions like these. How are the edges organized? How do the vertices differ among each other? Does it matter where you are in the network? What are the underlying patterns that describe the structure of this thing? And those questions are sort of proximate ways of getting at these deeper ideas, which are what processes shape the whole network, and how can we tell what process did it? Is it this process or that process? That's what we often are looking at, and trying to understand the structure of these complicated objects. In some way, it's like trying to coarse-grain an object. So if I have some complicated thing like this, I want to apply some function to it that then returns to me the major parts and also the degrees of freedom that tells me how those parts relate to each other. So I have some function, I apply it to a graph, and I want to get back these building blocks that tell me how this thing is organized. And that allows us to start answering questions like, how does structure and dynamics combine to make function? And these are really questions about the large-scale structure. I don't care about some tiny corner of the armrest of this chair. I care that there are armrests. And so this requires taking the network and not breaking it up into the tiny little pieces, but rather breaking it up into larger pieces, these coarse-grained units that allows me to understand how the whole thing is put together. So this is what community structure in my mind really means. We're going to take a network and we're going to decompose it into its building blocks in some way. But we want a fairly general definition of what it means to be a building block of a network, and the definition that we're going to use in this talk is this one, that we have a community that's going to be a set of vertices with the same pattern of inter-community connections. Now you may, if you are familiar with community detection, you may have heard of this notion that communities are groups of vertices with lots of edges among them and a few edges between them. Well, that is a special case of this definition, right? And I'll give you an example right now. If we have a graph like this, community detection would say, I want to find a way of labeling the vertices on this graph such that I have these groups that have these similar inter-community patterns of connection. So here's one labeling, which I draw these circles and I color them a certain way. Now I say, how does the orange group interact with all the other groups, including the orange group? And that allows me to write down this kind of community interaction matrix, in which the purple element tells me what's the rate of interaction among those types of colors. So in this case, this is an assortative community, meaning that edges tend to be inside the communities. And so as a result, the density is along the diagonal. So like connects with like. That's the canonical version of community structure that was introduced years ago. But this is a generalized notion because we can also represent different kinds of large-scale structures. So here's the assortative one, in which case the edges are inside the groups. But we can just easily have disassortative, in which case the edges are outside the groups. Okay. Or we can have something like an ordered structure. This would be like social networks in a grade school situation where like 7th graders interact with 6th and 8th graders, but definitely they don't hang out with high schoolers. So now you have this sort of ordered structure, in which case a group interacts with itself and then its adjacent groups. And then finally, core periphery structure can also be represented in this context, in which you have some communities that are in the core, and then you have this sort of progressive sparsification of communities as you move outward with the periphery. And so this notion of defining a community as a group of vertices that have a similar inter-community pattern of connections is very general. It subsumes the traditional notion, but allows us to talk about other types of large-scale patterns in the network. So there's been a lot of interest in this area, especially since 2000, although depending on which literature you read, there's been interest before that. There's dozens of algorithms, hundreds of papers, thousands of papers. It spans all fields. And one of the first ones was written by Michelle Gervin and Mark Newman, which I just checked has about 9,500 citations. So this has been a very active subfield inside the field of network science. But there's some troubles lurking in this field. And some of these troubles have been identified sort of early on, but not really investigated. But it's important, I think, to think about how these tools really get used in the real-world context. Like when you actually apply one of these methods to a real-world data set, what comes out? How do you understand whether or not that technique has told you something true or valuable or useful? These are important questions if we want to do science with them. So I'm going to summarize work from several different papers. This is one of the earliest ones I did in this area, in which we try to understand what are some of the failure modes of community detection. One of them, which is not due to me, is due instead to Fortunato and Bartholomew, is this notion of resolution limit. So modularity is one of the canonical approaches for quantifying how good a partitioning is. It's one of these assortative approaches, so it prefers to find community structure that's assortative as opposed to the other kinds that I described. But essentially what it says is that resolution limit says that modularity has a preferred number of edges to put inside groups. And that means that it has a hard time finding groups that are more sparse than that. They're smaller and more sparse. And so it can miss things as a result of this sort of preference that's built into it. There's no parameter in the modularity score that tells you how big a community you want. You can introduce it using what's called a resolution parameter, but that tends to say that you want all your groups to be of a certain size. It doesn't really allow you to find things of wildly different sizes. So that's definitely one potential trouble, that we might miss some things that are actually true in the network. Another one is that, so that's the math for it. Another one is that there are actually extreme degeneracies in this modularity function. So if we have a nice objective function, it's nice and convex, and there's a single peak, and maybe it's convex like this, and so the peak is really, really tall. Okay, so if we find that peak, we know that it's way better than any other partitioning we can find. And in fact, in modularity, we don't have that at all. Even for a network like this, just a ring network, this is what the top of the function looks like. And I'm not sure about you. I think that's the peak right there, maybe? It's hard to tell, right? Because the differences between the global optimum and the local optimum are very small. And if you apply this function to a network that is 1 million vertices, the difference between the global maximum and the second highest local optimum could be like 0.00001. I don't know about you, but that sounds pretty small. So what we find in this function is that there are an exponential number of competitive local optima, things that are not equal to the global, but are pretty close. And so if you have a deterministic algorithm, you're going to find one. Right? Your algorithm is going to climb up this surface. It's going to find some peak. It's going to say, I found it. Here's your optimum. And it will never tell you that there are all these other competitive optima around. And that's kind of a problem. If, in fact, whatever property you care about is representative across these different competitive optima, then it doesn't matter which one you find, because they all say the same thing. But if instead there is diversity, there's disagreement about the partition structure that these partitions return to you in terms of the network structure, then you're in trouble, because now your algorithm has sort of hidden from you the fact that there are these alternative patterns in the network. So this is not very good news, in fact. It says that we should be very cautious about looking at the output of the algorithms. Essentially, that true groups are likely to be merged in complicated ways. The reason you get this exponential number of competitive local optima is because I can take the small units and I can combine them in combinatoric ways and get something that looks pretty good anyway. Okay. So this is, if you want to do science with this, if say you're trying to find the modules in a social network or the modules in a protein-protein interaction network, this is really big trouble because it means that we can't reliably trust what comes out of one of these algorithms. Okay, that was part one of the troubles. There's more trouble in community detection land. Here's another thing that happens. So many networks have metadata on their nodes. These are things that we use to validate the algorithms, to check how well they're doing. The social networks, you have attributes of the people, like age, sex, ethnicity, or race, etc. In food webs, you might have like feeding mode or the mass of the species. On the internet, maybe the data capacity of the computer or the physical location. With proteins, you might have something like the molecular weight of the protein or its association with cancers, for instance. All these things can be metadata that we can use to say, if I apply my algorithm to the network, and it gives me a partition as a labeling, and I compare the labeling that the algorithm produces to the labeling that the metadata gives me. And if the algorithm gives me labeling that's very close to what the metadata says, then I can declare victory and I can say that, yes, it's doing something that I know to be useful. So we're trying to extend method A, we find some partition P, and we ask, does it correlate with the metadata X? And if it does, then we say success. And we have lots of stories in network science literature about this. Here's the infamous Zachary Karate Club with its labeling of the two partitions that came out of the schism between the president and the instructor. The political blogs network between the left and right blogs. Then you have things like the NCAA 2000 schedule. These are football teams and which conference they play in. Political leaning for books on Amazon. There's more. There's grassland species. This is the type of species you are. So like, let's see. The red ones are plants, I think, and the magenta ones are herbivores, and et cetera, et cetera. So different types of species. And then even on metabolic networks, you can also partition and figure out something about the groups of metabolites. So this has been done sort of across disciplines, and it's a standard approach that we use to evaluate how good our algorithms are. So in some cases, it seems like the science supports this, right? So we apply an algorithm to a network, we look at the groups, and we say, oh yeah, this makes sense. This helps us understand the science. Maybe it's about allegiances or personal interests in social networks or biological function in metabolic networks. There have definitely been success stories in which case applying community detection algorithms to these network data have produced something of value to science. But there are some recent studies that claim that this is the exception and not the norm. And that they say that either real-world networks don't contain structural communities or they exist, but they almost never correlate with what the metadata says they should be. So this also seems like big trouble, right? Because if my algorithms can't find the thing I'm trying to get out of the network, then what use are they? The evidence for this comes from this nice paper by Santo Fortunato and his collaborators, in which they took a ton of networks, a bunch of different community detection methods. The networks each have this metadata associated with them, so that means they can score how well each algorithm does at recovering that one. And they definitely include some of the canonical ones, the Karate Club, Football Network, etc. And then they have a bunch of other ones, so like Facebook Snapshots, DBLP Network for Computer Science Photography, Amazon, Flickr, Orca. But a lot of these are online large networks. And the results of this are that on the classic data sets, these over here, the y-axis here scores how close the recovered partition is to the metadata. So a high value says that they're very close, a low value says that they're quite different. So on the classic data sets, the algorithms all do pretty well, which is good because that's what we use to design the algorithm in the first place. So we have selected on that variable to make sure that the algorithms succeed there. But then on these other data sets, they all sort of fall over. They're not able to find a partition that correlates very well with the metadata that we wanted them to find. So this is trouble. It says that maybe these algorithms stink in the real world, right? They're either not real communities to find, or there are communities but they don't correlate with the metadata. Okay. Trouble. I tell you, trouble. So there's some problems. The problems are real communities can be merged by the algorithm in these complicated ways. We may not notice that they have been merged, and as a result, we don't identify the real communities. The best partition can get lost inside this exponential number of competitive local optima. As a result, we might not realize that we didn't get the best one, and we got some random partition that may or may not correlate with what we want. And the groups that we find don't correlate with the vector, the metadata that we were trying to recover. So this basically sounds like community detection is a bunch of hogwash, and we should all go and work in a different area. I think that's what it is. But there is hope. There is hope. Here's an idea, right? So we know that there are a lot of partitions. What if we use the metadata to help us pick the one that correlates with the metadata? Not only pick the metadata partition, but use both the network and the metadata together in order to search among this exponential number of competitive local optima to find the one that does what we want it to do. In other words, let's turn this into more of a supervised learning problem, as opposed to playing this sort of gotcha game where we design an algorithm and we give it a network, and then we say, aha, look, you didn't do what I didn't tell you were supposed to do. So we're going to use a generative model approach to do this. I like this because it allows us to move from the model to the data and then back to the model. So we can use a model with some parameter choices to generate synthetic data, and then we can check whether or not the model can infer the right parameters back from it. So this generative model approach is quite powerful. It requires specifying our assumptions up front if we're going to do this. We have to define this parametric probability distribution over all networks, probability of G given some parameters theta. And then if we're given our theta, then we can draw as many graphs as we want from this. Or if we're given G, then we can choose some theta that makes G likely, either in a likelihood or a Bayesian kind of sense. Okay. And we're going to use the stochastic block model because the stochastic block model implicitly represents this general notion of communities that I introduced to you earlier. It's very simple. It says that each vertex has some type. I have up to k types. Think of them as like colors. And I have this mixing matrix theta that tells me how the different types mix together. So this matrix right here would represent a choice of theta that captures a sortative structure, in which case I have high parameters along the diagonal and low parameters off the diagonal. And then I just say that the probability that some edge exists from U to V is just equal to the probability that those types are connected. Okay? So this is a notion of structural equivalence in some stochastic sense. And it directly captures the notion that in this definition of community is equal to vertices with the same pattern of intercommunity connections. So in this case, the orange community is defined as being something that doesn't connect with purple, doesn't connect with green, doesn't connect with blue, but does connect with orange. And this is a k by k matrix, and any k by k matrix is fine. So the definition of what an orange vertex could be any selection of probabilities in this vector. And that defines what it means to be an orange vertex. And in the community detection context, I'm going to learn what those vectors are. Okay. So how are we going to embed the metadata into this? We're going to use the metadata to guide the process, but only if the metadata is useful. So we're going to use the stochastic block model. We're going to define some more terms. Here's the metadata. I have some x value for each node u. I'm going to use the degree information as well. I'm going to make this a degree corrected stochastic block model, which has been shown empirically to be a pretty good model of real-world data, in part because it allows you to capture heterogeneous degree distributions, which are ubiquitous in networks. So then we're going to assign to each node a community S with some probability. So we're going to have a probability model that says, given your metadata, here's our prediction of what community you fall in. And then given what community you fall in, that then determines the network structure. That then predicts the edges. So we're going to take the stochastic block model, which is normally a model of the edges, and we're going to glom onto it this prior probability model that tells us how to predict the communities from the metadata. Okay. So that's our prior assignment. We're going to say the probability of being in some group S depends on this mixing matrix that tells us how the metadata types mix across the communities in the metadata. A very simple model here. And then we're going to use this degree correction trick in which we say that the probability that U connects to V depends on the mixing between the types correct for the degree of those vertices. So it's a degree corrected stochastic block model that uses the metadata labels as a prior on the community structure. Okay. So we can turn this into a complete inference problem. It separates quite nicely. We have a term for the network probability and a term for the metadata probability, and then we just use an expectation maximization algorithm to fit this model to the data. The nice thing about this algorithm is that it gives you two different matrices that you can interpret. One is this theta matrix. That's the way the groups mix with each other. That tells you what is the definition of being an orange vertex. Well, it's how I interact with all the other things. And then it also gives me this matrix gamma, which tells you what does it mean to be in community orange in terms of the metadata. Oh, if I have these kinds of metadata values, then I tend to be an orange vertex. Okay. So both of these things can be useful in terms of scientific interpretation. Okay. We'll see these in a little while. I'm going to skip over the details of how we do the inference because it's a bunch of technical stuff. And instead, I want to demonstrate that this actually works really well in practice. So does this method recover structure in synthetic data that we know is there? So we want to do a controlled situation. So we're going to use what's called the planted partition model. This is a pretty standard evaluation technique in the literature. What we're going to say is we're going to start with two groups, k equals 2. We're going to make them equal sized. We're going to set the mean degree equal to this quantity, c equals cin plus c out divided by 2. So these two parameters then allow us to vary how crisp the communities are. So with cin equals c out, there's no distinction between who I connect to, whether they're in or outside my group. Whereas if cin is very large, then c out must be very small because the average degree is fixed, at which point the groups are really crisp. There's not many edges between them. So this gives me a little mixing matrix here, and the question now is, can we recover this structure? Okay, well, we need to add some metadata. So we're going to choose a vector, a metadata vector, and we're going to set its correlation with the true groups. There are only two groups, so we're just flipping a coin here, at some value of 0.5, which means there's no correlation between the metadata value and the group assignment, the true group assignment, all the way to 0.9, in which case, most of the time, the metadata value agrees with its true underlying group assignment. And then we're going to vary this difference, this cin minus c out. Okay. So one detail that's important is that there's been theoretical work to show that there's a phase transition that occurs in this particular problem. So as the difference cin minus c out shrinks, as the difference between the two communities becomes more fuzzy, there's a sharp threshold below which you can't distinguish the two communities at all. Okay? So this is what's called the detectability threshold. So there are communities that exist there. There are differences. One, nodes tend to connect preferentially with things inside their community, but there's no algorithm that can recover that. So this is an information theoretic boundary. Okay. So what does that look like in practice? Like this. So along the x-axis, I have my cin minus c out. Here I'm fixing the mean degree to be 16. So when cin minus c out is 15, like almost all the edges are inside the group. And so the ability to recover all the correct labels is really high. This blue line represents this detectability threshold. Okay. And as I shrink the number of edges that are inside the groups, here's the phase transition here, which it occurs at a particular value, which is given by the equation in the previous slide. And below this point, you can't do any better than chance. Right? So you're just flipping a coin at that point, at 0.5. Okay. So the blue line shows you what happens if there's no correlation between the metadata and the true groups. Okay. So we just recover the classic detectability threshold behavior. Okay. So now what happens if we increase the correlation between the metadata that we observe and the true ground truth communities underneath? So each of these horizontal lines would represent how well we could do if we just ignore the network. So we're just going to look at the metadata, we're going to guess that that's the correct community structure, and that correlation value tells us how often we do well. So at the 0.9 level up here, 90% of the time the metadata tells us what we want to know. So if we just guess the metadata, that's how well we'll do at guessing the ground truth, it's 0.9. So a naive algorithm here would say, well, if I am better than this horizontal line, then use the edges, because I can do better recovering the ground truth using the edges. But if the blue line is below this horizontal line, ignore the edges and just look at the metadata. So for this magenta line here, that behavior, that algorithm would follow this curve and then have a sharp point and then go horizontal here. Okay. So that would be an algorithm that does as well as you could using only one of the two things, but being smart enough to know which of them to use at the right point. So that's our sort of baseline algorithm. We can do better than that with our metadata guided stochastic block model. Then we are somehow combining the information together in order to do better than either of these two things could do alone. So what does the results look like? Looks like this. So deep in the undetectable region, when the structure is so sparse that there's no information essentially in the edges themselves, the algorithm correctly chooses the metadata automatically. It realizes the edges are crud. I'm just going to use the metadata. And then out here, deep in the detectable region where the community structure is really strong, it also says, the metadata, it doesn't give me any more information than I have already, so I can just perform essentially as well as I do with the edges. But what's key is that between these two extremes, in the regime where things are hard, and perhaps even a little bit impossible without metadata, we do better than either of these two approaches can do. So this is a really strong result. This says that this technique does better than either metadata alone is possible to do, or is theoretically possible to do with only the edges alone for these hard problems, the ones where the community structure is pretty sparse. Metadata gives us additional information, allows us to tell where the communities lie, even if the edges don't have that information in them directly. So it's helping guide our algorithm to find the right region of the suboptimal partition space, to find the things that do pretty well, even though we couldn't find them without the metadata guidance. So this is a really nice result.
So did you try to do some scaling or
Some scaling?
like overlapping the curves and finding a critical distance?
No. Although you can, by eye, you can sort of see that there's still this sharp point that occurs, and it seems to be moving in sort of this direction. And we don't actually have a theoretical result that allows us to say how that point moves as a function of time. In part because generating this figure took 2 months of compute time on 30 computers. And that's because in this region, it's really hard to find stuff. And so the EM algorithm has a loop inside of BP, and that doesn't converge very often because the edge structure here is just really, really sparse. So in order to explore this numerically is a challenge. Mark and I have had some conversations about this, and he believes without evidence, I have to say that in today's day and age, he believes without evidence that there is no real phase transition anymore once you have the metadata. But we haven't explored that completely. And I think that that's a very interesting theoretical direction to go in, which is if I have additional auxiliary information in my network, can I somehow circumvent these hard theoretical boundaries for detecting this kind of structure? Okay. So that was nice. That was synthetic data, right? So we knew what to expect. What happens when we apply it to real-world networks? So we have 5 examples in the paper. I'll show you 3, which one of these I think really has a nice point to it, which is this one. So this high school social network, it's about 800 students from a medium-sized American high school plus its feeder middle school. So we expect this data to implicitly have this ordered structure in it because typically 12th graders are not hanging out with 7th graders. So we have 3 metadata variables. We have grade, ethnicity, and we have gender. And so this plot over here has all that information in it. It has the lightness of the color tells you is it middle school or high school. Darker nodes are high school. Lighter nodes are middle school. The shape tells you the gender, and the color tells you the ethnicity variable. And there are some variables for which we don't have a metadata value for the ethnicity. And so if we use the grade data, so we pass the algorithm the network, and we tell it the grade information for the metadata. It finds this partition. Okay? So light colored vertices over here, dark colored over there, high school, middle school. So if we ask it to find 2 groups, it finds 2 groups, and those groups correlate with the grade structure. The NMI, the normalized visual information, the agreement is pretty high for the middle school to high school partition, which is great. Okay, so it did the job we asked it to do. We said, find me a partition that correlates with this metadata, and it did. If you don't if you don't give it the metadata and you ask how well it does at finding the partition that correlates with the grade structure, instead you get a much lower NMI. So the metadata really is guiding the process here. Oh, but you might say, oh, it's just giving you back the metadata you showed it. Right? That's possible. Generally good result, I'll come back to the point in a minute. This generally good result also happens to be due to ethnicity, so now it finds a partition between the black students and the white students, regardless of whether you're in middle school or high school. And the NMI here is also pretty high, and compared with no metadata, it's pretty low. Okay, so clearly the metadata is shaping what it returns. But what if it's just giving us back the metadata? Okay, well, we have one more metadata variable, which is gender, and here's what happens with gender. Now it says, nah, I can't find a partition that correlates with this. And so instead it returns to you a mixture of the previous 2 partitions. The NMI between this mixture and the metadata variable is almost 0. So the method is smart enough to be able to say, these metadata don't have any correlation with the network structure. And so I'm going to ignore them and instead just look at the edges. If you just look at the edges, then it finds this mixture of the other two partitions. Okay. Now, why is it the case? Yeah, go ahead.
So why do we have different NMI without metadata in different situations? Shouldn't they have same NMI?
You mean in this case?
Yeah.
Well, that's because the target vector, the metadata vector, is changing, right? So in this case, the grade vector is different from the ethnicity vector in the other case. And so the degree to which I correlate will depend on what the target is. Okay. So why is it that in this network, gender does not correlate with the network structure? Has anyone ever used the AdHealth data? So there's this thing, apparently it's a technical term called a name generator. This is this form that they hand to the student and they say, write down the names of your closest friends. Well, in the AdHealth survey, they have two parts of that question. They say, name your 5 closest male friends and your 5 closest female friends. And so by construction, gender does not correlate with the edge structure. And so, in fact, this is exactly perfect for us, right? We wanted some metadata variable that doesn't correlate with the edges. By construction, they collected one for us. And presto, the algorithm is smart enough to ignore it. So this is nice. The algorithm is not just returning us the metadata if the metadata is garbage. If metadata does correlate with some aspect of the communities, it will find me a partition that correlates with both the edges and the metadata. So this is a really nice result. It tells us the method is smart. This is all the categorical data. We can also generalize it to work with continuous metadata. Excuse me. So this is a food web predator prey interaction from the Weddell Sea in Antarctica, about 500 species. We have several different types of metadata. I'll just show you results for the body mass, which is continuous. Now the function that we learned the prior uses this combination of Bessel functions, and so you can get this nice distribution that tells you, as a function of body mass, what's the distribution of mass over a particular group. So group 1, which is down here, is mostly small things with a couple of larger things. Group 2 is things that are mostly in the middle, and group 3 is things that are mostly big. And so in fact, we have recovered a partition that correlates with the body mass variable, which happens to span 21 orders of magnitude, because some of the things down here, primary producers are like algae, super tiny, and some of the things up here are like whales, which are super big. Okay, and then finally, we also applied it to malaria gene recombinations, which is an area of research that I also work in. So in this case, these are genes from a particular set of these are alleles from a particular set of genes in malaria parasites, and edges here represent genetic recombination. So when malaria parasites reproduce either sexually or asexually, they typically use recombination to shuffle the contents of these genes, because these genes are used in immune evasion in the host. And so if it's a random network, then that would imply that the reshuffling, the recombination between genes is also random. So here our goal is to try to identify non-random patterns in the recombination of these genes. So previously what people had done is they had applied community detection algorithms to this, and they found that indeed you can get some partitions, but they don't really correlate well with these metadata variables. So these cis-Paul V labels, these are information related to an adjacent part of the genome. So these are like how many cysteines are in this label for the gene and so on. So this is not data that's actually embedded in the network itself. But the malariologists believe that this information is important for correlating with different types of pathology, so cerebral malaria or the lethal kinds of child malaria and so on. So the previous result had been that we can't find a very good correlation that's reliable between the labels and the network structure. But using the metadata SVM, we can find a really nice partition. So this is a place where previously we were getting lost in this diversity of possible partitions, and the metadata was not being used to guide that process. But now, with using that to guide it, we can find the right region of space that has a good partition that tells us that indeed these cis labels that the malariologists believed to be important for separating different kinds of pathological outcomes are in fact highly correlated with the recombination structure. So it's sort of a nice confirmation of the hypothesis in the science. Okay. All right, so let's step back a minute. We sort of surveyed a bunch of things. We've seen these troubles, this notion that there's a lot of different partitions. We can't find the right one. Metadata doesn't correlate with what we want it to. The algorithms can't find the right partitions. And then I showed you this algorithm that allows you to use the metadata to guide the process. And so this I think should make us question, what's the goal of community detection in the first place? What are we trying to do? And I think that a lot of people would believe that this is the goal. Right? We have some network, we have some method, we apply the method to the network, and that produces some communities. So community C is F applied to G. And then we compare this to our metadata, and we ask, did it do a good job, right? Do the communities here correlate with the metadata there? That was the premise of the Crick paper that I showed you earlier. And that's been sort of the basis of the comparisons that we've been using in this field for a long, long time. But there are some problems, right? So if we succeed, we find communities who correlate with metadata, we say, yeah, publish. This method works well. But if we don't find the communities that correlate with the metadata, we say, oh, this method stinks. In this case, this is the karate club, this is the social partition, and this is what the stochastic block model returns to you if you apply the SBM to the karate club, which is it finds these 5 nodes in the one group and everyone else in the other group. And this seems like a bad outcome. And those of you who work in this field, you've probably had this experience. You write down some new algorithm, you're like, oh, this is brilliant, it's a great idea. You apply it to some of your test data and it fails. And you're like, ah, okay, maybe it wasn't such a good idea. But maybe you were too hasty in tossing out the good idea. Because in fact, there are 4 things that could be going on in the event that we find that the communities we find don't match the metadata. So the first possibility is that the metadata are unrelated to the network structure. And we saw some examples of that in the middle part of the talk, in which I designed it that way. The metadata was random compared to the network. That's one possibility for why your algorithm doesn't recover a partition that correlates with metadata. The metadata are irrelevant. Another is that they capture different aspects of the structure. So in the karate club, this partition corresponds to the social groups, but this partition corresponds to leaders and followers. Each of these nodes, these 5 nodes, are the highest degree nodes in the network. And so this is not wrong, it's just different. Another possibility is that there's no community structure in the network. And we also saw some examples of that in the middle part of the talk. In which case, you can't find communities to correlate with your metadata because there are no communities. And then finally, it could be that your algorithm actually is better. So any of these things could be true if you have this disagreement. This could also be true. But in general, in the literature, if you look at what people have written, you talk to people who work in the field, this is the only thing that they've considered. Is that if I get disagreement between my what's so-called ground truth in my communities, then clearly I am not doing a good job. My algorithm is poor. Okay, so we wrote a paper that tried to understand what's really going on here. And we came up with 2 theorems for community detection. And we're pretty excited about these because it's hard in general to come up with theorems in network science. And the first is that there's no bijection between ground truth and communities, meaning that if I have some data generating process, little g, I embed some ground truth in it, I can produce a graph, capital G. But I can have a different data generating process and a different ground truth and produce the same network. And as an example of this, think of the karate club, right? There are 2 partitions, the leader-follower and the social partition. These are 2 ground truths. And I have 2 different data generating processes that produce exactly the same graph. So there's no bijection between the communities I find and the ground truth, because I need to know the data generating process in order to disentangle these things. So we shouldn't try to believe that we can always recover the right ground truth from a given network, because there's no bijection here. And then the second one, which I really love this one, this is a no free lunch theorem for community detection. And this idea comes from machine learning, originally in the 90s, I believe, maybe the late 80s, by David Wolpart. And here we adapted it and applied it to community detection, showed that it works here. And it has a very simple statement, which is that no algorithm F has better performance than any other algorithm, F prime, when you average their performance over all possible inputs. This is true for community detection. It implies that there is no best algorithm. And so we shouldn't try to find it. An implication of this no free lunch theorem is that there's a distinction between general learners and specific learners. So specialized learners. So if you have a general task, you're trying to explore your data, you should use something that's very flexible, like the stochastic block model, because it can fit all different kinds of community structure. And it'll do a pretty good job on whatever problem you ask it to do. But if there's a specific kind of community structure you care about, like say a sortative structure, or if you're working with a particular kind of network, like say protein-protein interaction networks, then you can design a specialized algorithm that will outperform any general algorithm on that subclass of problems. Because that specialized tool will perform worse than you expect on some other input. Because the assumptions of that tool don't match the behavior of the data. So a general tool makes very weak assumptions, and so therefore it will do pretty well on those things. A specialized tool makes stronger assumptions, and therefore those assumptions are not met, it does more poorly than you expect. So that means that, yeah, go
If
ahead.
there is no free lunch in community detection, what's the cost you pay to get community?
Sorry, say it again.
What's the cost you would like to pay?
The cost. What the? I'm saying.
Okay.
Lunch.
Oh, what's the lunch?
How much is the
What
lunch?
is the added advantage you can add to get the community detection? If there is no free lunch, okay, what's the cost you want to pay?
Oh, okay. So the cost is that if you want better performance in one class of problems, you must accept worse performance on a different class of problems. So that's the trade-off. If you want to do better at recovering, biological modules and protein-protein interaction networks, then you're going to do worse on some other class of networks. So good performance really comes from matching the algorithm to its preferred subset of inputs, because it's going to do better there.
But
And
then,
so you shouldn't try to apply that algorithm to an input that's not what it expects.
but then the validation fails, right? What we want to do is we make an algorithm, want to work on information networks, biological networks, like we want all those big tables, blah, gamma.
Cannot be done. Not universally. There is no free lunch. Instead, you have to pay for your lunch by having worse performance somewhere else. So this question of what are the classes of inputs for which our algorithms do well on is not known. We don't know what are the set of inputs that a given algorithm does better on and then sacrifices its performance on other algorithms. We don't know that question for almost any of our algorithms. We can say a few things. So for instance, modularity assumes that the community structure is assortative. So if you pass a network to modularity that has ordered structure or core periphery structure, modularity will not do very well, because we know what assumptions it includes, which is assortative structure. So the reason modularity is done pretty well is because we've typically only applied it to social networks, which typically have assortative structure.
So but metadata could come from other community discovery algorithms, right? So you talked about this algorithm which has stochastic block model, and then it uses these different metadata and picks the right one to find the partitioning. Well, I can have my metadata come from all these other different community discovery algorithms and have SVM pick the right metadata, which would be the right objective function or the right set.
There is a notion in machine learning called stacking, which is a really cool idea, which is I have a bunch of specialized learners, and I pass some input to them. I run each of the algorithms on this input, and they all give me some scores. Can I learn which algorithm does better on which input based on the features of the input and the features of the algorithm? And this is how the Netflix challenge was won,
Yeah.
right? Which was combine a bunch of not so good algorithms, but then add a meta learner on top. I think that's a good idea. I would like to see more of that.
Well, we did that.
Oh, you did? Excellent. Excellent. Before we did this, I'm sure, actually. Okay. So take home message. Don't try to find the ground truth. There's no ground truth. I should put the karate club in there. Okay. All right. So conclusions. So the trouble with community detection is that there is really no ground truth, and we've been sort of misled by this notion of how we should evaluate our algorithms, right? Instead of this metadata is not ground truth, it's just more data. It's a different kind of data. It could be noisy, it could be biased, it could be wrong, it could be the output of another algorithm. It's just more data. So this notion that we should use the metadata as a way of deciding if an algorithm is good or not, that's totally wrong. We have been spending 15 years doing the wrong thing when it comes to evaluating our community detection algorithms. Instead, we should be evaluating them based on what we use them for. We should define some downstream task that says, well, I want communities because communities are useful for me doing something else. Well, how about I just find communities that help me do that thing, as opposed to trying to find communities using some objective function like modularity or stochastic block model. So we should turn this into more of a supervised learning kind of context. Because good performance depends on what you use communities for. If all you're doing is data exploration, then it kind of doesn't matter what algorithm you use. And you should use one that is as general a learner as possible, which probably means something like the stochastic block model. Okay. So metadata is more than just data. We can use it to select the structural communities that correlate with the attributes if they exist, because it's more data. It's not ground truth. And then I showed you this metadata-aware stochastic block model, which we think is a pretty nice tool because it allows you to solve this multiplicity problem of the different partitions that you could get by using the metadata to guide that process. So there are some future directions here which I think are pretty interesting. I mentioned, we've written it briefly, this phase transition. We don't know if the metadata eliminates it or simply defers it. That would be one interesting thing to look at. There's been some other work done on incorporating other auxiliary information into the detection process. Things like if I have a temporal network and I want to find communities that are changing slowly over time, then that means that there's information in the past and the future that can help me make an inference at a particular point in time. It turns out that this is right. Like if the communities have some persistence over time, you can use that to infer communities even in the undetectable regime to some degree. So the general question is, to what degree can we use this auxiliary data, auxiliary information, in order to try to guide this process to get communities out that are more useful? There's lots of applications here, I think, in part because the past work may have overlooked some important discoveries because we were using the wrong objective function to evaluate techniques. And we could just apply it to all the data and learn all the science. But then there are also extensions. So right now there are techniques with stochastic block model that work with temporal networks. That's it. Well, can we add metadata to that? What about if we have attributes on the weights on the edges as well? We'd like to be able to use that information. And right now we have tools that are good at using this kind of auxiliary information and that kind, but we haven't sort of mushed them together to get the most general learner possible. The no-free lunch theorem does tell us, however, that that algorithm, while it will be very flexible and very, very versatile, will probably not be as good as some specialized algorithm that you can match to the assumptions of the data. And then there are probably lots of other things that you can do in this space. So I want to thank my collaborators, Mark, whose work featured in the middle part of the talk, and then Dan Larimore and Ludo Peel for the ground truth about metadata, and then the original work identifying the sort of multiplicity of alternative partitions that are very good was done with Ben Good and Eva DeMonjoy. And thank you very much.
So I have a question about what you learn from community detection if you're feeding your answer into your process. So I mean, if we're trying to see if, let's say, the Karate Club split, shows up in some pre-split metric, and we use the after the split, groups to help predict that community structure, then what do we really learn about Karate Club? Like, have we really learned anything about what factors led to the splitting, or whether the split would have been predicted before it split?
Have you read Zachary's paper?
No.
It's a great paper because it includes a community detection algorithm in it. And this paper was published in 1977. Also, it turns out that there's a typo in his paper. And there are two karate clubs because this is an interesting era of time. He published the adjacency matrix as a figure in the paper. And it's not symmetric.
Okay.
So there's a 1 on the upper triangle that's not in the lower triangle. So now you have some ambiguity. And it's not clear in the rest of the paper which one is correct. Is it the 0 here or the 1 here? Anyway, that's somewhat as a tangent. Zachary was interested in these questions of what factors and what processes allow me to predict from a structural point of view what might happen in the future in terms of this split. And he didn't answer the question completely, in part because he didn't collect all the kinds of data that we would want to collect today. Things like the weight of the tie or the attributes of the vertices and so on. Instead, all he had was the ties and this partition at the end, along with the leader and the president and the instructor. And so if your goal is just to write an algorithm that can recover the metadata partition, then all the work that's been done in the past 15 years is fine, because that's how they've been evaluated. But that implies a weird kind of selection effect on algorithms, because we only publish algorithms that are good at recovering a certain kind of metadata. But what if you have 15 types of metadata? Now you need 15 algorithms. And so I think that in some ways, metadata recovery just doesn't make much sense as the ultimate goal in community detection. I think that instead, you should think carefully about the downstream scientific questions, right? So the communities are always, almost always, a piece of some larger scientific question. So if you want to understand what factors led to this partition, then the partition is data. And so then you would want to put the factors, which are probably attributes of the vertices, into the algorithm and ask how well this imagined algorithm is going to predict this kind of partition. That's a very different kind of task. That's a specialized learning task, because that algorithm is not going to work very well on a protein-protein interaction network, because the reason the partitions exist in the PPIN are different from the reasons they exist in the social network. So I think that really the message here is that we should think more carefully about why we're doing community detection in the first place. If the goal is just metadata recovery, fine, it's well-defined, you can knock yourself out. But I don't think that's really what we care about. I think that we really care about using the community structure for other scientific questions.
So one of your motivations early on was that the modularity maximization task is highly non-convex in a really obnoxious way. Is that less true of the likelihood function in your modified stochastic block model, which can in principle also be highly non-convex and obnoxious?
It is also highly non-convex. We don't have a way to quantify the degree to the non-convexity and so on. What we can say is that in practice, with non-trivial networks of non-trivial size, and you ask it for more than 2 or 3 communities, then it's highly non-convex as well. There are lots of local algebra. But if the network is small and you're only asking for 2 groups, then often the shape likelihood function is more nice. But as we saw, even with the high school network, we only asked for 2 communities, and even there were enough different partitions that the algorithm could sort among, that it could find ones that correlated with this metadata or that metadata.
Yeah, is there an intuitive mathematical story about why we see that nice performance, given that we don't have quite so much control over the non-convexity of the algorithm?
Sure. Well, let me try to describe a picture. So imagine I have some likelihood surface that is obnoxious in some way, and I'm now going to convolve that with some convex function. But the location of that convex function, I'm going to move. Of the peak. The location of that peak is the metadata. So now I take these 2 functions and I combine them, and that lowers the likelihood of some things and raises the likelihood of others. So that's why the algorithm is finding things that correlate with metadata, because I've made them more attractive in some ways.
So what fraction of the metadata is available as it matter, like compared to the size of the network? So that's kind of like tilting the landscape in a sense.
Yeah. Well, so in some sense, our synthetic experiment did that. So in this case, each of the nodes has a metadata variable attached to it, but the degree to which it correlates with the ground truth is a random variable. And so down here, essentially the metadata is irrelevant. It's just some random noise. And as we move up these different lines, we're making more metadata available for it. And so it's able to get more information out of that. In practice, if you want to apply this to a network in which you're missing metadata for some fraction of the nodes, you just give them a new category of metadata that says missing. And the algorithm treats that as just another metadata label.
So how do you learn the strength of these correlations between metadata and so what are these little dots?
So we learn this matrix here, which is composed of these things. So this is a little gamma variable indexed by S and X. So S represents the number of communities, so 1 through K, and X represents the metadata values, which should be 1 through L, for instance. So we learn each of these parameters, and we do this using our likelihood function here. So we're just effectively maximizing the likelihood over all the different parameterizations of this matrix.
for example, if you have like two types of label data, one is for example for gender, the other one for weight.
Yeah.
They both play a role, but one is a little bit stronger than the other one. So probably I have like bimodals, like one local minimum, one is probably higher than a little bit higher than the other one, but both of them are kind of like interesting questions.
Yes.
But then it's kind of like crucial how much metadata you gave it to the model, so that, for example, if like gender is weaker, but we want to find the model of gender, so like how much you have to give the metadata so that it tells the landscape so that the gender is higher than.
So in this case, we only give it one metadata variable at a time. So one extension for future work would be to write down a model in which, instead of having these categorical variables for metadata, you have these vectors. So that allows you to combine multiple metadata vectors into a single model. In our case, we would either give it the gender or whatever the ethnicity was. And we would ask it to find me a partition that correlates with the one that we showed it. If you want to ask this question of which one of these things is stronger, then there's a way to use these tools to do that, but it's not really elegant. I would rather essentially replace this model, which is just a model for predicting a discrete variable from some input, with something else, like regression, or an SVM or something like that. In fact, this right here is a general thing. You could replace it with any machine learning model you want. So in that case, then you could learn a regression function that allows you to estimate the coefficients of the relative importance of the gender and the ethnicity variables for predicting the community structure.
But is it that like finding both of the local minima is a very interesting question than which one is? I mean, is it interesting to just rather than finding one like minimum? The question should be find all the local minimas that is relevant, and then try to understand what it means.
I agree. That's an interesting question, and that's not the question this algorithm is solving.
Okay.
Last question.
Curious about what you think of in the sort of an interplay between this metadata where stochastic block model as a good way to describe the network that you observe, but also as like a way of maybe how the network is itself generated. So if the nodes come in with some sort of metadata aware like preferential attachment, I'm moving to a new city and I want to connect with these types of people that are similar to some metadata that I'm preferentially attached to.
Yeah. Yeah.
Could there be a sort of mutual or circular process in that?
Yeah, I mean, one way, if you have multiple dimensions and you're trying to understand the relative importance of these things, then if you apply the algorithm to each dimension individually, and then look at how well the partition you get correlates with the metadata, the one that it correlates the most with, like that sort of gives you weights on the importance of these different things. I mentioned that this is sort of kludgy. A better way to do it would be to replace the metadata model with something that allows you to do it in one shot, which is to say, I want to learn a model over all the different dimensions of metadata that predicts what partition I go into. And then you have weights that are interpretable, and that will tell you that like, location is more important than gender. So as I said, you could replace this model here with essentially any machine learning model. Right? You could replace it with an SVM, you could replace it with random forest, you could do anything like that. You might have a harder time doing the inference steps there. But in terms of defining the model, we're just trying to predict this latent variable, the community assignment, from observed things. And then given the latent variable assignment, then we generate the edges. And so there are constraints on what S is from both types of data, from metadata that I see, and also from the edge that I see. Okay, thank you very much for your attention.